All right, polyprotic acids have more than one acidic H, and each H will have a separate Ka value. The first one will be the strongest, followed by the second, followed by the third. Typically, if you're dealing with polyprotic acids, the difference is big enough that you can ignore the second or the third because it's so much weaker than the first one. The exception to that is sulfuric acid. The first hydrogen in sulfuric acid is strong, and so you want to use that as the H3O plus for the second ionization and go from there. So let's look at some polyprotics. I mentioned sulfuric. The first one is strong, and then the second one is still quite significant. Other ones that you're likely to run into, phosphoric acid has 3 acidic hydrogens, and you can see that their Ka values differ by quite a bit. First one times 10 to the minus 3, second one times 10 to the minus 8, third one times 10 to the minus 13. So there you go. The other one, carbonic acid, H2CO3, is another one that you'll run into with some frequency. So let's practice. What is the pH of a 0.12 molar solution of carbonic acid, H2CO3? The first Ka value is 4.3 times 10 to the minus 7. The second Ka value is 5.6 times 10 to the minus 11th. And you can see that these two Ka values differ by several orders of magnitude. So we're just going to ignore the second one and work through the first one. So we're looking at H2CO3 in equilibrium with H plus HCO3 minus. We have a 0.12 molar solution. So we're going to lose some, gain. And again, if you look at my Ka value, we can do the X is small approximation. And so my 4.3 times 10 to the minus 7 is equal to X squared over 0.12. I can solve for my X. So I get an X value of 2.27 times 10 to the minus 4th. And then if you think about that, that would be your H plus concentration in the second ionization. And if your H plus is that high, you're going to push back towards the products. So when your equation here is HCO3 in equilibrium with H plus CO3 2 minus, and we already have a 2.27 times 10 to the minus 4th, 0, and 2.27 times 10 to the minus 4th, you're not going to get a lot more H plus from that when the K value is so low. So we're just going to use this as our H plus concentration. So then our pH is the negative log of that. So we get a pH of 3.64. Flip through a couple of these slides. We can use the approximation. And we get a pH of 3.64. That was a lot of slides to work through all this math on, but we got the same answer. Okay, what about sulfuric acid? That's the one where you do have to worry about that second value. So let's just work through a problem with it. It's going to be simpler. So find the pH of a 0.0100 molar sulfuric acid solution. So what we do is the first one goes to completion. So we're going to use our initial concentration as the concentration of our HSO4 minus and our H3O plus to start with. But then because we don't have any SO4 2 minus, we're going to gain that. So at equilibrium, we're going to be gaining X. Now we're in a situation where we can't use the X's small approximation. We're going to need to solve the equation. Our K value is 1.2 times 10 to the minus 2. That's from the previous slide, is equal to 0.0100 plus X times X divided by 0.0100 minus X. And there you need the quadratic equation. If you do that or plug it into something like Wolfram Alpha where you can solve it, you're going to get an X value equal to 0.0045. So that's from the quadratic. Again, you won't be expected to do that on a test. You won't need to use a quadratic equation, but I do expect you to be able to get to here. And then that gives me my X value, and so my concentration of H3O plus is 0.0100 plus 0.0045, which makes it 0.0145 molar. And then if you take the negative log of that, you get a pH equal to 1.84. There we go. Look, 1.839, 1.84. So again, you can see that the second ionization did change that concentration from 0.0100 to 0.0145. So significant change. You need to take it into account with sulfuric.